thickness and same dye concentration and so forth. And so we can compare the results of this one and this one directly. Then we found in this pipeline case, the threshold was almost one order of magnitude lower than DCM. So one of the reasons why many people use DCM is the excitation wavelength. You can use the second harmonic generation of Yak laser. That is almost the peak of DCM. But in this case, the absorption peak is more UV region. But anyway, the threshold get very lower compared to DCM. And another interesting thing is, in this case, transition dipole is along this direction, not this direction. So the lasing occurs at the higher energy edge, contrary to the normal dye. So this is another example. So the anthracene and pyrene has the different dipole with respect to the nematic dielectric. In pyrene case, the transition dipole is perpendicular to the nematic dielectric, but in pyrene case, anthracene case, transition dipole is along that direction. Is parallel to the nematic liquid crystal. So in this case, lasing occurs at lower threshold, but in this case, lasing occurs at lower energy side, higher energy side. So that is another difference. We collected all the data of threshold and what is the key factors to have the lower threshold. That is, of course, we have to have a high quantum efficiency. So in the pyrene case, quantum efficiency is more than 0.85. DCM case like 0.4, something like this. And we have to have a high absorption coefficient, and the solubility of dye in crystalline liquid crystal. This is also important, and the large radiative decay rate. So the collection of all these data shows these are the important factors. So we are still continuing on developing new kind of dyes to achieve lower threshold. So far, we found another derivative of pyrene that gives the very small threshold compared to DCM. So we are still expecting new dye molecule. And the nice thing about low threshold is that if we have a low threshold, then we need low excitation power. That means the stability of dye becomes better. Okay, so this is almost the end. Finally, I want to, since there are many students, I want to tell you something. These are the measure the discovery in our lab. We found the antiferroelectric liquid crystal in 1989, and the people in liquid crystal, people believe that the liquid crystal molecule tend to align parallel to each other. But this is different. the molecule align in a zigzag fashion. However, actually, this kind of structure was identified by many people. And the different discoveries, the bent core molecules. And it is, people believe that the bent core molecule is not good for liquid crystal, but actually not true. This gives a variety of phases and a variety of interesting physical phenomena and so forth. So this is actually a treasure island of liquid crystal science. So what I want to say is discarding the conventional wisdom is sometimes the first step toward attaining new discovery and understanding. So that is the message to young people. And last but not least, I want to advertise our new journal, NPGAZ Materials. We launched this journal about 2 years ago with Nature Publishing Group, NPG, and Tokyo Tech. And the purpose of this new journal is to advertise the activity of material science in Asia and Pacific countries, of course including Australia and New Zealand, because more than 30% of material research output coming from Asia and Pacific region, but we do not have any material-related journal from this region. So we launched this journal. And this journal has the 3 phases. The first phase, we publish about 20 research highlights per month. So we have about 50 advisory members in Asia and Pacific region. They recommend a good paper published in this area. Then, after voting, we decided which paper should be highlighted. Then, science writer in Nature write a highlight article and then publish on web. And the last October, we started the phase 2 that include a review article. We publish 3 review articles quarterly. And of course, the final target is to publish the original papers from all over the world. This is the website, and this is free access. So if you access this site, you can freely download every highlight article and also review articles. And the situation is quite good now. And this is the point that we publish the review article, and number of access increases suddenly. And the region of access, this red is from Asia, of course, and this blue and yellow is from America and Europe. So even from the outside of Asian countries, we have many access now. So please take a look at the website and enjoy the articles. Okay, thank you very much for your attention.
Okay, questions? Yes.
I have a question. I was wondering if there would be an advantage of using quantum rods or dots, instead of dice in those kind of systems that you could see.
Yeah, we are trying to use, yes. Of course, many people are now trying to include the content dot. And so we need some chemistry, of course, to dissolve the content dot in crystalline liquid crystal. But of course, it's important.
There have been some papers, in particular from Taiwan, I remember, in nanoletters, where we got quite high this, concentrations of rods dispersed and influence patterns. And another question is, so, you show how you can get the defect mode glazing, and so in those cases you would insert some layers of either isotropic or pneumatic material. And the other possibility perhaps could be having line defects. I was wondering if there is any advantage of using those, in particular line defects rather than, so this is one-dimensional photonic crystal, right? So you can imagine having some sort of a dislocation defect, right? So do you foresee something interesting happening in this case?
I've never thought about this, but thank you.
I have a question. It concerns your experiment regarding the reduced threshold when you put the extra dye in there, the transfer between the two dyes. You said that the reduction in the threshold was to do with reabsorption. I'm not quite sure if that's true. I mean, is the estimated absorption cross-section, sorry, is the absorption cross-section for the two dyes the same? Or I thought that the sensitizer, if the sensitizer dye has a stronger absorption cross-section, and if the quantum efficiency for the energy transfer is near 100%, then that would lead to a lower threshold. So I'm not really quite sure whether, and reabsorption would occur in both cases, so I'm not quite sure whether that's a valid.
Yeah, I have the same question. The energy transfer is not perfect, of course. So efficiency must be lower than the director.
Well, it depends upon the if the absorption cross-section for your sensitizer is higher, and the quantum efficiency for the energy transfer is near on 100%, then you would expect a reduced threshold with the sensitizer, like we have. So I'm not really quite sure. I mean, if the lifetime of the sensitizer is also longer compared to your lacing iron, in this case the other dye, the DCM dye, then you'd also expect a reduced threshold. So the fact that you're getting a reduced threshold with the incorporation of the sensitizer is not unexpected if the properties of the sensitizer are better as an absorbing species, a better chromophore than the lacing dye. So perhaps.
So yeah, it depends on how efficient the energy transfer occurs.
Well, it must be occurring very, very efficiently. It's a resonant process because you've got the absorption and emission spectra overlapping. So he says it's a Foster process, and a Foster process, basically the energy transfer is proportional to the overlap interval between the absorption spectrum and the emission spectrum. The emission spectrum of the absorbing species and the absorption spectrum of your lacing species. So it's unexpected that you're getting a reduced threshold. But anyway, you can talk offline if you like.
In addition to our report, there are the previous report from 2 or 3 groups. So it is true. And,
I don't disagree it's not true, but I think I understand why it's true. Yeah, more questions? Yes?
You give some advantages for the application for the micro lasers inside the RGB. Other applications?
Other application of micro laser.
Is it in shape or?
So at this moment, in the practical level, I think one of the laser I introduced is the spatial gradient, the crusted liquid crystal with spatial gradient. If somebody needs any color laser beam, then we can use the crusted film with spatial gradient. Then by hitting the different part, we have blue, green, blue, red, any colors. But of course, the dye lifetime, the dye is not stable enough. So after several uses, we have to dispose. So a kind of disposable use is, I think, in the practical stage. But for the long-term use, we still need to stabilize the dye, and that is the very important and very difficult issue. As you know, the normal dye laser case, if we keep the dye in the cuvette, then it will decay very fast. So in this case, we confine in 10 micrometer thick, like 10 micrometer thick. So the dye is damaged very easily. So that is a very important point.
Mostly to use nano crystals, I mean, for the material.
Yeah, of course, if you have the periodic structure, we do not need to use a plastic liquid crystal. But in this the plastic liquid crystal, we do not need to fabricate. So the plastic liquid crystal, spontaneously forms the periodic structure. That is the advantage. For instance, to make a large area display surface emitting lasers.
No, I mean, instead of using the dye for the game, you seem to
Yeah,
use
he
yes,
already mentioned the content
or
of.
no, I mean, such as medium yak, and then you can make it very tiny. Like nano scales, and then you put it in. It's
Nanoscale emitting material.
such as solid state crystals, such as medium yak. When you stretch it on some processing, you make it like a nano scales.
Yeah, that itself is nanoscale.
Yeah, but that is the lifetime is not very long. So
Yeah.
But you don't get the tunability though with neodymium YAG. You don't get the tunability. Neodymium YAG's got a very narrow spectrum of emissions, so you're not going to get the tunability the same way you get the tunability with the dyes.
that's the advantage of the dye.
That's right.
Yeah,
You're right, you get the storage efficiency as a result of a longer lifetime perhaps,
Yeah.
but you don't get the
Yeah.
tunability. I think Hideo's work is all about tuning.
Yeah. But the lifetime is not very longer given because the fate of the dye.
Sure.
For the nanocrystals, it can be used for a long time.
Okay.
I mean, not quantum dots.
Right, yeah. Okay, good.
For instance, European derivatives that gives a very sharp emission, and we also try to use such kind of element.
Okay, do we have any more questions? If not, can we thank Hideo again? Okay, so back here at 10:30.
And